Okay, a quick review today of geometric sequences in series. So just to look at arithmetic, we're adding or subtracting constant values to certain terms to create a pattern. Today we're going to look at patterns that have a constant ratio or multiple between them. For instance, 1, 2, 4, 8, and so on. I'm doubling every time. So there's still a ratio, we call that R. That's our new letter. That's the only new letter we have today. Okay. Obviously a new equation, geometric sequence, un equals u1 times r to the power of n minus 1. N is your number of terms. U1 is still your first term. Un is still your general equation or the nth term. The only trick is you have to find r. To find r, you can always take the second term divided by the first term. So for this example up here, 2 divided by 1, r would be 2, or any other consecutive terms. So if I took 8 divided by 4, it's still 2, right? Any consecutive ones. And always take the bigger term, so term number 4 divided by term number 3, or 3 divided by 2, or 2 divided by 1 will always give you your r value. Okay, let's look at some examples. The seventh term of a geometric sequence is 108. The eighth term is 36. Write down the common ratio. So this is taking that idea into play right here. So U8 over U7, they're consecutive, one after the other. I get 36 out of 108, which is a decimal, or better version, a fraction. Okay, keeps the fraction exact rather than rounding off the decimal, makes life a little bit easier. Let's find U1. U1. Okay, so I'm going to take my equation and plug in some things that I know. For instance, I know that U7 is 108. So 108 occurs when I have an n value of 7. I'm going to take my information from right here. N is 7, the term value is 108. I'm going to solve this. I'm going to solve this by simplifying, okay, and then taking my handy-dandy calculator and dividing by that number. So rather than trying to work with all the decimals, I just left it as 1/3 to the power of 6. Type in my calculator the way it looks, and you should get 78,732, I believe. Okay, now that we got U1, we got U and R, we can find any other term. So I want to find U number 4, fourth term, 78,732 was U1. R is 1/3, 4 minus 1. You can simplify your exponent, make it a 3 if you want to, just to make it easier to type into our calculators. And I got 2,916. And then D, the last term of the sequence, is 4/3. How many terms are in the sequence? So we did one of these yesterday. And if I know the last term, I put it as my UN. I just have the rest of the equation. Nothing's changed here. The only difference is I have to solve for n. Now, there's a couple ways of solving this. I'll talk about 3 of them, I guess. There's the algebraic way, where I'm going to divide out 78,732 and do the same thing over here, which gives you 1 over 59,049. I'm left with 1/3 to the n minus 1. And the way we can solve this like an exponential equation is make your bases the same. If you make your bases the same, that means the exponents have to be the same. In other words, if I keep that the same, I ask myself, what exponent do I need on 1/3 to make it into 1 over 59,000? Guessing and checking exponent rules. I'm trying to make my 3 basically into this, right? That works if I use a 10. Well, if the bases are the same, that means the exponents are the same, and I can solve the exponent. If you don't like that idea, we can actually go back to the beginning if we wanted to. And using our graphing calculator, we can find a POI between those two equations. Here's y1, here's y2. Solve that, figure out where they meet. Again, they'll meet at 10. I'll get the graphing calculator in a second when we do some other ones. Or third option, if you've used your simplified version like this one, we can use logarithms. I can guess that's what most of us will do. So I'm going to take the log of 1 over 59,049, or whatever decimal that happens to be, equals the log of 1/3 to the n minus 1. And based on log laws, we bring our exponent down front. And on the left side, I still have this log, 1 over 59,049. And I can solve for n by rearranging here. The log of my top fraction divided by the log of my bottom fraction will leave me n minus 1 and 10, which looks suspiciously like the green one up here. And n is 11. Okay, so some choices there. I don't care which way you use. IB doesn't care which way you use. You like logs, use logs. We do that whenever we want an unknown exponent. We could use this idea of the base is the same. That's the green one over here. I can use that because I know it has to be a pattern in the sequence. It has to be a whole number exponent. I usually use logs when I don't know what kind of exponent I'm going to get. And we can use a graphing calculator, of course, also y2 and y1, plug them in, figure out where they intersect. And as I said, I'll get the graphing calculator in a minute to do some other questions. We can talk more specifically about that if you forget how to do POI. Okay, let's get some more examples. The annual fees paid to a private school for the years 2001 and 2 are shown as a geometric progression in this table below. Calculate the common ratio for the increasing sequence of fees. Kind of our standard question. We want to find R. As we mentioned, R can be found between any two consecutive terms. So easiest ones I'm going to choose would be these two. So 8320, the second one, over the first one. I divide that out, and I end up with 1.04. There's my R value. The fees continue to increase in the same ratio. Find the fees paid for 2006. All right, so UN equals U1, that's 8,000. My R is 1.04 to the n minus 1. So I want to find 2006. The only trick here is to think about what U number that is, because it's not U6. It's actually U7. And the reason why is U1 ends in the 0. U2 ends in a 1. U3 ends in a 2. So U, what would end in a 6? It's got to be 7. That's one less than it every time. Okay, so just be careful there, because if you move the wrong exponent in, it won't work. Okay, so we got 7 minus 1, which is the power of 6, and you should end up with $10,122.55. And because this is a money question, we should go dollars and cents. Part C, in what year did the cost approximately $11,841.95? Okay, well, let's figure that out. C, I want to know when I hit 11,800 and what's the number there? 41.95. Knowing that it started at 8,000, R was 1.04 to the n minus 1. Okay, so this looks like the last question. So I showed you how to do with logs. If you want to use logs, totally fine. I'm not going to make my bases the same because I have decimals, and decimals are tricky. So here's a chance to try the graphing calculator out. Graphing calculator, how does this stuff work again? Well, once we turn it on, we're going to go into our y equals screen. We're going to type in our first number, 11,841.95. My second equation is 8,000, bracket 1.04 to the power of, we don't have n, so we'll use x minus 1. Now, it's not going to show our answer off the bat because our window is wrong. That's always the challenge with solving for an unknown exponent, is getting the right window. So if we go into window, we have to think about our x's and our y's. X in this case represents years. Well, our minimum number of years is 0. We can't have less than 0 years. I don't know how big to make the X max, so I'm going to call it 20 for now. I figure it won't take 20 years in the future to go up to 11,000, considering that U number 7 was 10,000 already. And my Y min. Well, my fee started at $8,000. That's the lowest it could ever be. They're not going to go down. They're only going to go up from there. My max, I need to look for when I get to 11,841. So I'm going to go a little bit bigger than that, call it 12,000. That way I know my graph will show the parts and pieces that I need. If I press graph, I get my straight line. That's the 11,000 one. Here's my fee structure going up. That's the 8,000 one. I want to figure out where they meet. To do that, second trace, we want that calc button. Number 5, and we're going to press enter, 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 because I want the first curve, the second curve, it wants a guess. You know, we just press enter there, and I get 10.999999, okay, and that is your n value, 10.99999, which is basically your number 11. Now be careful, the question said, in what year did that happen? So if n is 11, what year is that? Oh, remember when n was 1, it was the year 2000. So if n is 11, this will be in 2010. Your n value has always been 1 higher than your year value. And again, if you don't like that method, use logs. Logs are the fastest way of doing this one. And just to show again one more time, 11,841.95 divided by 8,000 will leave you with 1.04 to the n minus 1. We're going to take the log of the left, whatever this comes out to, the log of that big giant fraction there. It's a big decimal, so I'm not going to really worry about what it is. And I'm going to divide that by the log of 1.04. And I'll get n minus 1 left over there. It's the same process every time. And this should come out to 10 on this side, n minus 1 over here, and it's still 11. So either way, you get 11, right? Kind of the point. Okay, let's try another one. It's one of the trickier ones from last year. Okay. We did one of these with arithmetic sequences yesterday where we were given 2 terms. We could use some common sense there, and that's doable with a geometric sequence, but it's kind of hard sometimes. So when I'm given 2 sequences terms, like I have here, the second term and the 7th term, what I really want to do here is make more of an algebraic solution. So I've been told in the question, U2 is 4 and U7 is 12,500. What I'm going to do is I'm going to build 2 equations and use elimination to solve them. So equation number 1, 4 equals U1 times R. I don't know either of those things, but I know that N is 2. And the other equation is, I know the term value. I don't know U1. I don't know R, but I know the exponent is 7 minus 1. If I simplify these both, well, 1 here, I don't really have to show the 1, but there is a 1 there, and 12,500 over here, I get R to the 6. Well, if I take my first equation and I line it up underneath here, and I use elimination, I can actually eliminate the variables. To do that, I don't subtract or add in this case, because I don't have subtracting or adding between my variables. Right now, these 2 things are multiplying. The opposite of multiplying is, let's divide them. 12,000 divided by 12,500 divided by 4 comes out to 3125. U1 divided by itself, like this thing, comes out to the number 1. And R to the 6 divided by R to the 1, that's an exponent rule. Exponent rules when I divide is, I subtract. Well, now I can find R pretty quickly. I don't have to really worry about that 1 out front. So I need to worry about the R5. To get rid of a 5, we take the 5th root. And the 5th root of 5th root of 3125 is 5. Now that I've got R, I can go back to one of my original equations. I'm going to suggest maybe this one, because it's nice and easy to work with, and find U1. So 4 is 4, U1 I don't know, but I know R is 5. Hey, U1 is 4/5, or 0.8. Okay. The question was, what was the equation? Well, now I got the parts and pieces I need. So part A, all that math results in u1 4/5 times r to the n minus 1. Part B asks for term number 10. So let's look at u10. So 4/5 times 5 to the 10 minus 1. Plug it all into our calculator, and I ended up with 1,562,500. What you can get using your formula, or if you want to, once you figure out r, you can just keep going from the 7th term. The 8th will be this times 5. The 9th will be that times 5. The 10th will be that times 5. You could do that too, right? If you couldn't figure out the pattern, use your equation and keep on going. Oh yeah, that's sequences. Let's take a look at series. Did I pick that one out? I think I took that one out of your thing. Hang on 2 seconds. Let me pause this for a second. Never mind, I left this one in your box. Okay, we got one more, then we'll talk about series, sorry. Okay, the first term of an arithmetic sequence is 0, and the common difference is 12. So this question is reflecting back on what we did yesterday. Find the 96th term of the sequence. So, remembering yesterday, we're going to go back to an arithmetic sequence. So 0 plus n minus 1 times d. d is 12. Oh, I'm actually looking for the 96th term, so I can look for u96. So 96 minus 1 times 12. Punch into our calculator, and you should get 1140. Okay, part B. The first term of a geometric sequence is 6. The 6th term of the geometric sequence is equal to the 17th term of the arithmetic sequence above. Write down an equation using this information. So what do I know? Well, I know that u number 6 for the geometric one is the same as the arithmetic one. But it's the 17th term of the arithmetic one. So I'm going to have to find that. So 0, actually let's write it this way. u6 is actually equal to u17. u17 is 0 plus 17 minus 1 times the difference of 12. Into our calculator, 16 times 12 makes 192. Okay, so I know that u6 is 192 for the geometric one. I also know that the first term is 6. So what can I do here? I know that u6 is 192. So 192 will equal u1 times r to the n minus 1. But I know some more stuff. I know the first term was 6. Oops. 192. The first term was 6. I don't know r, but I know this is the 6th term. There's an equation that has that information in it. That's all they wanted. They wanted some sort of equation. They didn't ask you to solve it yet. They just wanted the equation. In C, we have to solve it, but we had to make the equation first. Okay, how are we going to solve this? I'm working on C now. 6 r to the 5. Well, I can divide both sides by 6 and get r to the 5. 192 divided by 6 is 32. Hey, I know how to get rid of exponents. I take roots. I want the 5th root, and r is 2. So that's kind of a combo question, right? Arithmetic things and geometric things at the same time. Okay, let's look at the series now. So again, like yesterday, sequences and series are joined together. Sequence is the pattern. The series is the sum of the pattern. To do geometric ones, we have one formula, just one. There's no shortcut. In the IB booklet, sometimes they write in the backwards format, but it means exactly the same thing. So pick the one you're comfortable with. This is the one we're familiar with. And we need the same parts and pieces, so U1, R, and N. And you just got to be careful about brackets and BEDMAS and all that fun stuff. So let's give this a try here. Determine S10, the sum of the first 10 terms in this pattern. What do I need? I need R. So I'm going to take term number 2, which is -9. Be careful, we need that negative. Divide by term number 1, I get negative 3. And let's go. U1, that's 3, times R. R is itself negative 3. And make sure I have that negative sign again. To the power of 10 minus 1 over negative 3 minus 1. Now, if you're careful with your calculator, you can plug that all in at once. If not, do the stuff inside the big bracket, square bracket, first. You should get 59,048 divided by negative 4, and it results in negative 44,286 if you've done it right. That's it. That's how you do a sum of a series. Let's do some problem solving. A geometric sequence has 1024 as the first term, 128 as the fourth term. Find the sum of the first 8 terms. Well, that would be doable if I knew what R was. But I don't know what R was, so I have to go back to the sequence idea. So what do I know? I know that I have a sequence with a first term of 1024, R to the n minus 1. I know the fourth term is 128. So 128 is my term value when n is 4. I can solve this. 128 divided by 1024, r to the 3. Okay, now that's going to be a fraction, obviously, or a big long decimal. It doesn't really matter what it is. Either way, I need to find r, which will be the cube root of whatever that number happened to come out to. And if you do it properly, you should get r as 0.5. Now that wasn't the question, it wasn't find r. It said find the sum of the first 8 terms, but I couldn't do that without knowing r. That's part of my formula. So u1 r to the n minus 1 over r minus 1. Into your calculator go, either multiple steps or all at once. You should get 2040. Part B, find the number of terms in the sequence for which the sum first exceeds 2047.968. So 2047.968 is the sum. What else do we know? We know what, well, I know what R and U1 are. 1024, R is 0.5, but it wants to know how many terms it takes to get to there. So I have an equation to solve. Here's where I can use logs again, or graphing calculator again, your choice. Either way, I would simplify this before I start it. For instance, I might take 2047.968, and on this side, how about we divide 1024 by negative 0.5, right? That would make that a little bit easier to work with. So we'll end up with negative 2048. I still have 0.5n, I still have minus 1 inside the bracket. Now I can divide out the negative 2048 and the negative 2048. If I'm using logs, that's what I have to do. And I'll be left with, on the right-hand side, 0.5 to the n minus 1. The bracket's gone now. And over here, I'm going to get, I don't know, this big, ugly, messy number, right? I don't really care what that number is. I'm just going to leave it as a fraction. 20.968 over negative 2048. Okay, this is the log way. So what am I going to do next? I'm going to take the 1, and I'm going to bring it over here. It becomes a plus 1. All right, so now I've got 1, I don't know, minus whatever this fraction thing came out to. I'm keeping the fraction just because it's a big long decimal. I don't feel like writing out all the decimals. And on this side, I've got 0.5 to the n. Hey, that's my log time. I'm going to take the log of this stuff. I'm going to divide it by the log of 0.5, and I'll get n. And if you do that right, you should get 15.96 for n. That's the log way. Maybe this would be where the calculator comes in handy, because I can actually go back a few steps, way back up to the top in fact, and put that equation in kind of the way I want it. as in I can put all of this in at one time and find the POI. How's that going to look? Let's give it a try. So back to our equations. Clear that one out. 2047.968. Y2, I'll clear that one out. I've got negative 2048 bracket. This I can see here. 0.5 to the power of x over minus 1 bracket. Okay, I got to think about my window. My x's are my term numbers. I don't know how many terms I need, so I'm going to leave it 0, 20 for now. But I know my graph starts at negative 2048, and it has to grow to positive 2047.968. So if I wanted to, I could start in the negatives. Negative, I don't know, 2048. I need to go to at least 2047, so how about, like, I don't know, 2500. Let's pass that number. And we're going to graph it. There's our straight line. Here comes our curvy line. Hey, they meet somewhere along there. I want to figure out where. Second calc, 5, enter, enter, enter. And hopefully we get the same answer. Hey, we did, 15.96. Now we know we can't actually have a decimal term number. N can't be 15.96. So which term is it? This would be the 16th term. This is the first one, or sorry, the sum of the first 16 terms is required to exceed 2047.968. Okay, try the last one. It's a big one. It's a paper 2 question. The geometric progression, just a fancy word for a sequence, has 1 as its first term and 3 as its common ratio. The sum of the first n terms is 29,524. Find n. Okay, so this is kind of our standard question. Sum 29,524. U number 1. Our ratio is 3. Exponent is n. Subtract. This is basically the last question we just did, just with nicer numbers. Right, so how would we go approaching this one? Either logs or the graphing calculator. Your choice. Either way, I would make it simpler if I could. For instance, let's think of this number as a 2 on the bottom, and maybe this would be a good time to cross multiply. Right, 2 times this is 59,048. I don't really need to worry about the number 1 because it doesn't do anything. I've got that beautiful equation, which if I'm using logarithms, I've got that beautiful equation. The log of 59,049 now, divided by the log of 3 now is n. And I got n as 10. Okay, done the first one. Okay, more practice with logs or graphing calculator, your choice. Okay, a second geometric progression, G2, has the form 1, 1/3, 1/9, 1/27. State the common ratio. Well, that's easy enough. Take term number 2, which is this one, and divide by term number 1. That's just 1/3. Done. Calculate the sum of the first 10 terms of G2. We can do that as 10. We're starting at 1. Our common ratio is 1/3. I need 10 terms. I can divide by 1/3 minus 1. So I'm using my calculator one time, putting brackets around that bottom bit right there. And I ended up with, this is a decimal, my calculator can't handle the fractions, 1.4999 dot 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 dot, which to 3 sig figs is basically 1.50. Okay, E. Explain why the sum of the first 100 terms of G2 will give you the same answer as the sum of the first 10 terms when corrected to 3 sig figs. Well, what's happening at this point? At this point, we've actually rounded our last answer off to 1.50 because 3 sig figs, the answers, the parts and pieces that are being added are so small. And if you actually look at the next one, 1/3 to the power of 11 is so small that the value being added is always going to round off to 0. Okay, it's an explanation question. No math involved there really, just thinking about what is happening to these numbers. If I add that to this, I still get 1.50. Okay, last piece. Using results from part A and part C, or otherwise, kind of the standard IB lingo here, calculate the sum of the first 10 terms of this sequence. Now looking at this sequence, it looks messy. 2, then 3 1/3, then 9 1/9. It doesn't seem arithmetic, but it also doesn't seem geometric. In fact, the hint in this question is this. Using your values from part A and C. Well, if you look at A is the sum of the first n terms of G1, and there was 10 of them, right? Now think about that first sequence. What was it? It was 1, then 3, then 9, thinking about the common ratio, then 12, then so on and so on and so on. And in C, they get asked to do the first 10 terms. Interesting. Made up of this sequence. Well, what happens if you combine these two sequences and actually add them together? 1 and 1 makes 2. 1/3 and 3 makes 3 and 1/3. 1/9 and 9 makes 9 and 1/9. Well, that's what they're asking us to do right here. So what they want you to do is recognize that part A and C, the sum of the first 10 terms, has already been done for you. We know the sum of the first 10 terms of the first sequence was this. The sum of the next of the 10 terms of the next sequence was 1.5. So in part E, we're looking for actually G1 plus G2, so 29,524 plus 1.5. Just make sure I wrote down that number right. 29,524, yes. Which comes out to 29,525.5. Okay, so that's a recognized question. And the way you recognize it is they're trying to give you a clue. So using results from part A and C, you have to look back. Not a huge question, but you have to look back and figure out what they're actually trying to tell you. Okay, that's geometric. If you need some practice on some things, look at those. If you haven't looked at arithmetic things, look at those. If you need to do another video for tomorrow's lesson, I will do that also. But hopefully we'll be back to class tomorrow.